All right, so in this video, we are going to do a little bit of chemistry review and look at some chemical principles, because these chemical principles are going to be important in learning how bacteria and other microbes are going to grow on media and how we can control them, which is what we're going to focus in on this unit as well. So let's dive into a little bit of chemistry. So chemistry is the science that studies how molecules are formed and how they interact with each other. So why do we need to study chemistry if we're in microbiology? Well, microorganisms rely on complex chemical reactions, so how new molecules are formed or broken apart, and how they interact, which is called metabolism. And they do this in order to maintain an internal balance that we call homeostasis. And so this is why we have to review chemistry. So let's look at some definitions first. So an atom is the small unit of an element. These guys are used to form molecules, okay? These atoms do have what we call subatomic particles. These subatomic particles are going to include electrons, neutrons, and protons. Now, this should be review, but when we look at this, remember that electrons have a negative charge, neutrons have no charge, and protons have a positive charge. When we look at their mass, like how much they kind of weigh, this is going to be different per molecule. But protons and neutrons each have a mass of 1, and we call this AMU, atomic mass unit. So they're 1 each. Electrons are so small compared to these, atoms and protons and neutrons are also super small, but these guys are even smaller. We're going to consider the fact that they have 0 mass. Now, granted, that's not true, but their mass is so small, we're not going to take it into account. Now, where are these guys located? Well, protons and neutrons, if you'll notice in the picture, they're found in the middle of the atom, and we call that the nucleus. Now, don't get this confused with the nucleus of a cell, okay? But this is the place where protons and neutrons are found. The electrons are in this outer area that we call the electron cloud, and they form these energy shells, and they stay in those shells and orbit or go around the nucleus, right? And so that's our subatomic particles. Now, an atom has equal number of protons and electrons, and so if it's an atom, it's considered neutral. If I have 5 positives, I have 5 negatives. That means I have 5 protons and I have 5 electrons. So when it's an atom, it means that it's neutral, and the positive and negatives will equal each other. Now, there is something called the atomic number. The atomic number is found on the periodic table. It is the smaller number. This atomic number represents how many protons are found in the nucleus. So in the case here with carbon, there are 6. So there are 6 protons. Now, this is unique to every element. So if the proton number changes, the element changes, okay? Now, there's another number on here, which is larger, and this is the atomic weight or the mass. This is where we take the protons plus the neutrons, and that's going to give us that number. So we know that there are 6 protons, and so if you subtract 6 from 12, there are 6 neutrons here. You'll also notice, though, this is a decimal, and this is because it's the average mass of all of the different atoms. And so sometimes an atom might have more neutrons or less neutrons. It just depends, okay? And remember, neutrons are neutral, so the charge doesn't matter. It's just going to change the weight of the atom. So when we look at elements, elements are going to be found on the periodic table. All atoms of the same element have the same number of protons. Okay, so that is where if it changes from 5 protons to 6 protons, it changes from boron to carbon. So it's going to change the atom or that element. There are 92 naturally occurring elements. That means in nature, there's 92 of these we can find. However, there are a lot more on the periodic table now, and a lot of those are man-made that are over that 92. So let's take a closer look at the element. So when we look at an element, it does have an electronic configuration, and some of the ones that are going to be important to us are going to be what we call CHNOPs. We need to focus in on the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These guys are going to make up a lot of the molecules that microorganisms are going to need, and so they are significant here. When we look at this, no matter which one we're looking at, they do have an electron configuration where the first shell, the first one closest to the nucleus, holds only 2 electrons, okay? But shells out from that, shells 2, 3, they're going to hold what we call 8 valence electrons. Now, atoms and elements want to be happy and full, okay? In order to be full, each of their layers have to have the full amount, okay? So this makes them stable and inert if they are full, and those are found on the periodic table at the very end, and that's the noble gases. They have a full electron shell, and so they don't react. They don't react with other elements because they are content and happy. So when we look at this, electrons are going to fill from the inner shell to the outer shell. So the inner shell has to have 2, then the next one 8, and so on. Now this is simplified. If you were to take chemistry, you would obviously know that this is a more complicated concept, but we are going to look at it just as this rule of 8. So if the first one has 2, then the next one has to have 8 in order to be happy. So let's look at some of the electron configurations for some of these elements. And so if we look here at hydrogen, hydrogen is going to have a 1 atomic number and a 1 atomic mass, which means that the proton number is 1. And since it's an atom, our positive has to equal our negative. So if I have 1 positive, I'll have 1 negative, which means 1 electron. And then I will have 0 neutrons because 1 minus 1 is 0. So if we were to look at this particular atom, you would see that there's 1 proton in the nucleus and there's 1 electron in the shell. Now this is not happy because in that first shell they need 2. And so this allows hydrogen to react with other molecules. The next one is carbon. Carbon has an atomic number of 6 and an atomic mass of 12. Remember, the atomic number is the number of protons, so that is 6. And when we have an atom, the protons, positive, have to equal the electrons, which are negative, so there would be 6 electrons. And then we need to find how many neutrons are present. So we would take the atomic mass, which is 12, and we would subtract the 6 protons from it, and we have 6 neutrons. Now, you'll notice that they don't always have to be the same, where you saw hydrogen had 1, 1, and 0. But in a lot of our examples, we're going to see that the numbers are all the same when we're talking about atoms. So let's take a look at nitrogen. Nitrogen has an atomic number of 7, so that means it has 7 protons. Since it has 7 positives, it's going to have 7 negatives, so it has 7 electrons. And then we take the atomic mass, which is 14, and we subtract the 7 protons, which gives us 7 neutrons. For oxygen, our atomic number is 8 and our atomic mass is 16. So the protons are 8. If I have 8 positives, I need 8 negatives. So electrons are 8. And then 16 minus 8 is 8. Okay, so this is what we're looking at here. Now, of course, these don't all have to be the same, especially when we're talking about the neutrons, because neutrons are just changing the mass. If the neutron number changes, it's called an isotope. So if you look here at this oxygen may be oxygen 17 or oxygen 18. And so if you look here, we see that if it's 17, it has an extra neutron, so there would be 9. If it's oxygen 18, there's 2 extra neutrons, so this would be where there are 10. And these are considered isotopes of oxygen. Now, they're not the most common. Oxygen 16 is the most common, but we do see that there are different variations, and the variations are based on the number of neutrons, called isotopes. All right, so this brings us to looking at molecules versus compounds. So molecules are formed as a result of atoms that are chemically reacting together, and they're doing this in order to fill their outer shell. So remember, the first shell, they're going to fill it with 2. The next shell, they're going to fill it with 8, and so on. And so they're going to react until they can get that last shell full, so then they're happy and content. Now, when we look at the definitions here, there are 2 kind of definitions when it comes to molecule and compound, okay? So a molecule is when any kind of elements react together. But a compound is a molecule that has different types of atoms reacting together. So if we look here in this example, I have oxygen atom here. It's 1, so that's why it's called an atom. But when 2 oxygens combine together, we call that an oxygen molecule. Okay, so they can be the same or they can be different elements, but they can be called a molecule. So pretty much any kind of combination can be called a molecule. But in order to be called a compound, these have to be different. So if you look in the next example, we have oxygen bonding with hydrogen. Hydrogen is different than oxygen. So we can call this one a compound. So this is a water compound, or we could still call it a water molecule. Okay, molecule can be used all the time. Compound can only be used when they are different elements. Okay, so compounds can be referred to as molecules, but not all molecules can be called compounds. All right, so this brings us to the chemical bonds. How do they make sure that their outer shells are full and happy? So chemical bonds are formed between atoms when they chemically react together to help complete that outer shell. There are two types we're going to talk about that fall into this category. There are ionic bonds and there are covalent bonds. We are also going to talk about hydrogen bonds, but one thing to note is hydrogen bonds are between molecules, not between atoms. Okay, so ionic and covalent are between atoms. Hydrogen bonds are between molecules. So let's look at ionic bonds first. An ionic bond forms between atoms when they donate or they accept electrons to fill that outer shell. So one of the best examples of this is table salt, NaCl. So sodium, if you'll notice, in its outer shell has one atom. And in order to be happy with that shell, it would need 7 more. So if you look at sodium here, it has 1 electron in that outer shell. And in order to be happy, it's going to need 7 more electrons. That's going to be difficult. So what sodium decides instead is that it would be easier to give away its 1 electron. And if it does that, then its next shell is full. Well, this means it gave away a negative. So when it gives away an electron, it donates it. Now it has more positives than it does have negatives. This changes it from just Na to Na+. So it has a positive charge because now it has more protons than electrons. And we call this an ion now, not an atom. Now if you look at chlorine, chlorine has 7 in its outer shell. It only needs 1 more to be happy. So it takes or accepts the donated electron, and now its outer shell is happy. But because it has an extra negative, an extra electron, it is now an ion that is Cl negative. Okay, it is more negatively charged. Now, positively charged ions are known as cations, and negatively charged ions are known as anions. And what's cool about ionic bonds is opposites attract. So when you have a positive with a negative, they're going to be attracted to each other. All right, kind of like how with magnets, when you have a north pole and a south pole and they're opposites, they're going to attract. Same thing here. This is an ionic bond. The next type of bond is called a covalent bond. Covalent bonds are going to form between atoms when they share electrons to fill their outer shell. So they're not giving it away and donating it and accepting like we saw with the ionic. They're going to share. So in this case, hydrogen has 1 electron in its outer shell and it needs 2. So it can bond with another hydrogen and it can share those 2. So those 2 electrons will go around one hydrogen and then they'll go around the other hydrogen. And they'll keep doing that so that each of them has a chance to have a full outer shell. Now, if they are the same size and they are going to share equally, we call this a non-polar covalent bond. Okay, because of the fact that they're sharing equally. And you see that here when there is a line present in a covalent bond, it represents the pair of electrons they're sharing. So the 2 that they're sharing in order to be present there in that bond. Now, when we look at hydrogen bonds are formed between molecules. And so if you look here, in this water molecule, I have oxygen bonded to 2 hydrogens. And so in this particular case, they are covalent bonds because they're sharing. But oxygen is a lot bigger than hydrogen. And since oxygen is bigger, it pulls the electrons more often. And so since it does this, this creates what we call a polar covalent bond. So those hydrogens have a slightly positive charge and the oxygen has a slightly negative charge. Now, what did we say happened when positive and negatives interact? Well, they attract. And so if you put a bunch of water molecules together, they're actually going to be attracted to each other, where the hydrogens of one molecule will be attracted to the oxygen of the next molecule, because positive and negatives attract. These are known as hydrogen bonds. Now, they're very weak individually, but when you have a lot of hydrogen bonds put together, they can be pretty strong. So water has a polar covalent bond, and it has this between hydrogen and oxygen, but hydrogen bonds hold water molecules together. This is what makes water molecules stick together, stick to other surfaces, things like that. Gives the water lots of different properties. So let's talk a little bit about some of our chemical reactions. Chemical reactions involve the making and breaking of chemical bonds. So we either put the bonds together or we break them apart. What goes into the chemical reaction is called the reactant, and what comes out is known as the product. So in this particular case, for a synthesis reaction, so this is one where we are making bonds, we're going to take A plus B and we're going to bond them together to make AB. Okay, so we built it. This is synthesis. On the other hand, a decomposition reaction is going to take AB and break them apart back into A plus B. So this one is breaking the bonds, all right? So synthesis makes bonds, decomposition breaks them. Some other terms that go along with this is if we're talking about a synthesis reaction, this is known as an anabolic reaction. Anabolic means a building up. So we're building new structures. Whereas decomposition is a breaking down. So this is known as a catabolic reaction because we're breaking it apart. Another set of terms that can go along with this is that when we are building something, that requires a lot of energy. So energy goes into the reaction, and so we call that endergonic, energy going in. On the other hand, decomposition, since we're breaking it, we're releasing energy. Energy moves out. This is called an exergonic reaction. So think about exit. It's leaving, okay? That's what we're looking at for these reactions. So metabolism is the sum of all of your chemical reactions, the building and the breaking. So both types, anabolic and catabolic reactions, fall under the umbrella of metabolism. This is where the release of the energy in decomposition is going to be used to build new things in the cell for the endergonic synthesis reactions. So they go together. So let's take a little closer look at synthesis reaction versus decomposition. So a synthesis reaction is the building up of new molecules. This is known as an anabolic reaction. This is also known as a dehydration reaction. Now, it would be great if they just would use the same terms all the time instead of having all these other ones that fall under that. But they all describe things that happen during the reaction. Okay, so anabolic is the building, that's the synthesis. Now, the reason it's called a dehydration reaction is if you'll notice, water is removed. So if you look at the picture here, you have an H on one side and an OH on another. They form and water gets taken out as a product. So this is why it's called dehydration, because we are removing the water. So an example here is I have a monomer, which means one building block, and I have another monomer, another building block, and together they're going to form a bigger building block called a polymer. Poly means many. These are when you take like simple sugars and you build a more complex carbohydrate. Or you take those amino acids and you make more complex proteins. Or nucleotides and you make nucleic acids. Now we're going to talk more about carbohydrates, proteins, and nucleic acids in part 2 of this lecture. But this is the building of them, called the synthesis reactions. On the other hand, when we have decomposition, this is the breaking down of molecules. These are the catabolic ones. This is also known as hydrolysis. Now, let's look at the word hydrolysis. Hydro means water. Lysis means break. So you're going to add water to break the bonds. Okay, so this is where we have a more complex structure like a polymer, and we're going to break it back into those building blocks of those monomers. So it's the opposite of what we just saw. So complex carbs are broken down into simple sugars, proteins are broken down into amino acids, and nucleic acids are broken down into nucleotides. So decomposition reactions are opposite of synthesis reactions. Now, there are two other types of chemical reactions. They can be exchange reactions. Exchange reactions are where they switch partners. So like they're dancing with one partner and they switch and dance with another partner. So in this case, B and D switch. So AB plus CD switches into AD plus CB. Okay, this is a combination of both synthesis and decomposition because we have to break them before we can put them in a different order. Okay, so they use both types in this reaction. Another one is known as a reversible reaction. A reversible reaction is where one way it's synthesis, but the other way is decomposition. But they can go whichever direction they need. It's reversible. I don't just build it and it's always built. I can always break it down if I need to. And so these two are going to be where they can be reversed. A plus B can be put into AB. AB could be broken back down into A plus B. And so this is why the arrows go in both directions. It's reversible. All right, so I know this was a quick overview of chemistry, but there is going to be a part 2 where we're going to dive into those biological molecules that are important for living things. And so we'll take a look at those in part 2.